Okay, so what we're going to do right now is we're going to try to talk about the particle in a box. The situation is this. I have a particle which is confined to one dimension, confined to a line. We're going to set the regions of the box as 0 to A. Our variable is x. At 0 and at A, the potential energy goes from 0 to infinity. So we have infinite walls. We're going to set this up in 3 different regions. First off, we have this region, V of x is equal to infinity. In this region, V of x is also equal to infinity. In this region, equal to 0. What we need to do is we need to solve the Schrodinger equation in this region. So let's do it. H psi is equal to E psi. My Hamiltonian is minus h bar squared over 2m d squared dx squared psi. The potential is 0, so I don't include it, is equal to E psi. What I'm going to do is I'm going to consolidate my terms and rewrite this as a second derivative. So d squared psi dx squared is equal to minus 2m times the energy over h bar squared. All I've done is just take this term and divide both sides. So now I have a situation where I've got a function whose second derivative is equal to a constant times the function back again. I'm going to rewrite this as equal to minus k squared psi. And that's just going to help me out a little bit in terms of my mechanics here. So what I know that k squared is equal to 2me over h bar squared. What function do I have which meets these criteria? Well, I've got a couple of possibilities. But before I do that, I'm going to do these regions first. Region number 1, region number 3. What function, so if I solve the Schrodinger equation in those regions, what options do I have? In region 1, my potential is equal to infinity. So, minus h bar squared over 2m, second derivative of the wave function, plus infinity times the wave function is equal to 0. What possible function do I have that will meet this criteria? It's actually pretty simple. My function must be such that the wave function is equal to 0. So in region 1, the wave function is 0. In region 3, the same thing holds. The wave function is equal to 0. In region 2, I'm left with the second derivative of the wave function is equal to minus k squared psi. I need to solve for psi. What function is it that gives me whose second derivative is equal to itself times a constant? I can think of a couple of different possibilities here for my possible functions. My first possibility is either sine kx or cos kx. The derivative of sine is cos, the derivative of cos is minus sine. Same thing for cos, I'll get that. The other possibility is e to the I kx or e to the minus I kx. I can put my solutions in either form. I'm going to stick with the real form right here, sine and cosine. And so what I'm going to do next to solve for my wave function is I'm going to write this as a linear combination of sine and cosine because I don't know which one is going to be the case. So my wave function is going to be, is a function of x, is going to be equal to a cos kx plus b sine kx. What I need to do for solving a differential equation is I need to take a combination of the possible solutions and then solve for my boundary conditions. I'll get to those in a moment. So here's my possible solution. Psi of x is equal to a cos kx plus b sine kx. Now I mentioned boundary conditions. These are quite literally, what are the values of the wave functions at the boundaries? My first boundary condition is that psi of 0 must be equal to 0. The wave function must be continuous. And because the wave function must be continuous, I know that the wave function must be 0 right here and right here, because that's what it is from regions 1 and 3. So, if my wave function is equal to 0 at 0, there's only one possibility here. At x equals 0, sine kx is going to be equal to 0. Cos kx, however, is going to be equal to 1. And what that means is that a is equal to 0, my wave function is equal to b sine kx. Again, I was going to rewrite k, but we have it up here. We can see that k then is equal to square root of 2me over h bar. Okay. That's my first boundary condition. What do I use as my second boundary condition? Well, my second boundary condition is that psi of a must be equal, which is equal to b sine ka must also be equal to 0. In other words, equal to b sine square root of 2me over h bar times a equal to 0. Now, there's only one possible solution. Well, several solutions here. Namely that, so b sine ka must be equal to 2n pi, where n is equal to 1, 2, 3, 4, etc. So that's my boundary condition. If I meet this, we can see this, so at sine equal to 2 pi, sine 2 pi is equal to 0. Sine 4 pi is equal to 0. Sine 6 pi is equal to 0. So this condition is my second boundary condition. So what do I now have? I put these together, and my final wave function, my solution, sine of x is equal to b sine n pi x over a. That is my wave function for the particle in a box. Okay. When I talk about our next talk, we're going to talk about energies and how do we solve for the energies of the particle in the box.